Hello everyone. Okay, so today we will be going over chair conformations. What is a chair conformation? Equatorial versus axial, stable versus unstable, and cis versus trans. So after this, you will be able to turn a cyclohexane into a chair conformation and label the more stable ways to draw it. So what is a chair conformation? Well, it's called a chair conformation because it looks like a chair, and it is basically a cyclohexane. So you can take a look. This is how we're used to drawing it, and you're going to turn it sideways because a cyclohexane is actually not planar, and planar means flat. So when you flip this to the side, it is not just a straight line. It actually is going to bend. And the reason it's going to bend is because there is not nothing here. On these ends here, there are little hydrogens, and they are all in each other's space, and it is very crowded. So the ring is actually going to bend, so that way it is not so crowded. And how is it going to bend? Well, I have a 3D image here to help. So if you look at this is what we're used to seeing, the classic cyclohexane. And during a chair conformation, you're kind of going to take that and you're going to flip it. So see how this, it's flat, and then you turn it sideways, and it's actually not flat anymore. It's kind of bent. This side is kind of pointing up, and this side is pointing down. So we're going to figure out how to transform that. So how do we draw it? We're going to take a line. There are two ways to draw it actually, and you can draw a line. So we're going to draw two lines. I'm going to draw two different chair conformations. So one line here. One line we're going to put a little bit behind and then go a little further out. The other one we're going to go a little bit ahead. There you go. We're going to go straight up, straight down, and notice how I left a little bit of space. The lines, it's not a box. There's space. And then you'll close that space but with kind of like a triangle look. So remember, you're going to go down, up, and then close the triangle. So these are two different ways to draw a chair. And that is what this ring is going to look like sideways. So it can become that or that. So if you like, you could take a second to practice drawing it on your own. Okay, moving on. So how do we draw substituents on a chair conformation? Well, there are two different directions that it could go. It could go up or down. Now, what do I mean when I say up or down? Well, when we draw a chair conformation, the hydrogens, there's two hydrogens on each point, right? And they can either be going up or down. Or they could be going sideways. Sideways will be in this direction. Now let's bring back our 3D model. So if you notice, these are the ones that go up. Oops. So there are some that go up, directly up, like these ones here. Directly down, like these ones. And then some go sideways, but they're not completely sideways. This one is tilted up a little bit, and this one is tilted down. So how do we do that on the chair conformation? It can be a little bit daunting, and you do not actually have to memorize it. So the ones that are going directly up or down are called axial, and the ones that are going sideways are called equatorial. Okay. Remember, equatorial ones are sideways, and they can be tilted a little bit up or a little bit down, so they're not completely sideways. So when I draw a chair conformation, I like to draw the axial ones first, so the ones that are going directly up and down. So you start on the point, and I make this point go directly up, and then the next one will go down. Up, down, okay? Now, if you notice here for the cyclohexane versus this cyclohexane, chair cyclohexane, they both have 3 carbons, of course, because they're the same thing. 6 carbons, because they're the same thing. So we're going to circle them, and I'm going to label them for clarity. So let's go 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. So I hope that helps you visualize how they are being moved. Okay, and now we can draw the equatorial ones. So when there is an axial hydrogen going up, we want an equatorial hydrogen to be going in the opposite direction. So remember, it's sideways but not totally sideways, so we're going to draw it sideways with a little bit of a down tilt. This one is going to be sideways with a little bit of an up tilt, down, up, down, up. See? And that's it. You drew a chair conformation. So we can go over the steps again, just for clarity. So 1, draw chair shape. 2, draw axial substituents. Number 3, draw equatorial substituents. Now, a side note, when you're drawing the axial substituents, I usually start at the point. The top point, the point going upwards, like this one here, and I make it go up, so that way it's all unified. Okay, now what about the other way? If you guys would like a practice, I will give you a practice problem. So draw the substituents for this ring. Okay, so you can pause the video here and give it a shot. Alright, so how are we going to do this? So first we already drew the chair shape, so now we're going to draw the axial substituents. So we're going to go down, up, down, up, down, up. Okay, now the equatorial substituents. Remember, opposite direction. So this one's up, so down, up, up, down, up, down. Okay. Remember, on the end of these, there will be a hydrogen. Now, for the next bullet point, we have to see what is stable versus unstable and cis versus trans. So as review, what is cis and trans? So cis means same, and trans means opposite. Okay, so when you have a cyclohexane, ones on the same side will be either both wedges or both dashes. So if we have these, are these two hydrogens cis or trans? Actually, we'll make them chlorines. Are these two chlorines cis or trans? They are cis. Okay, and trans will be opposite. So we will have this, this. So this means that they are different directions. So one will be going up or down, they cannot be both going up. Alright, so how do we draw this for the ring? Now remember our process. So our process is draw the chair. Down, up, down, up, down, down. So now we've drawn it. And we will want our chlorines to be going in opposite directions. So I will pick one that's going down. And remember, you have to be conscious on how far apart they are, because this is the same thing as this, it's just turned sideways. So when I'm doing substituents, I think it's helpful in the beginning to label the carbons. So 1, 2, 3, 4, 5, 6. Okay, so we know that the next chlorine has to be right next to the other chlorine. So 1, 2, 3, 4, 5, 6. Okay, so 1, 2. Okay, so we know the other chlorine has to go here. Now these are trans, so do you think it will go up or bottom? That's right, it will go up. So that means that which one of these lines is facing up or facing down? This one is axial down, and this one is equatorial up. So we are going to pick the equatorial up because it is the opposite direction, because this one's equatorial down. So for short, I'll write E down, and this one is E up. Now remember, this works for axial too, so you could also do axial up and axial down. Now with this one, where they're the same, to give it a little bit of extra spice, I'm going to move one of the chlorines over here. So remember, you're going to want to label the carbons, and you only have to do the labeling until you get more comfortable. Eventually, you'll just be able to visualize it. So I'm going to label these here. 1, 2, 3. And remember, they are cis, so they're going to go in the same direction. So this one is going to go, I'm going to make this chlorine go down. So this is down, this chlorine is down. And then I'm going to make this chlorine, it has to be down. So that also happens to be equatorial. So this is also down. And therefore they are the same. Now, how do we know which one will work better if they're different? Which conformation will be more stable? So in an ideal world, we want as many things to be equatorial as possible because that is the most stable. So equatorial is more stable compared to axial. Axial is less stable. But as you just saw, sometimes things have to go in a certain direction. Like if they're trans, they have to be in opposite directions. So how do we know which one to make axial versus equatorial if we don't have a choice? The bigger one is the answer. So the bigger substituent equals equatorial. So we are going to try to get as many of the big substituents equatorial as possible. So I am going to change the substituents here. So what if we have a methane? So let's make a methyl group. So a methyl group, if we draw it out, chlorine is just one atom, but a methyl group is going to have little hydrogens on it. So it's more branchy, it has more stuff. So it's going to want to be equatorial because it's bigger. Okay, so then when we draw this, we can draw the methyl group first. So remember, I'm keeping the carbons aligned, so I'm drawing this on the 1 carbon, and I'm going to draw equatorial. And then when we draw the chlorine, they are going in the same direction, so it has to go down. So we can't make it equatorial. It has to go down because the methyl is going down. So we have to put it axial.